Hi friends, welcome to my channel TechnoBuzz. In this video, I will discuss how to set up an overset or overlapping mesh in OpenFoam. I will discuss this procedure in 4 videos. This is the first part. If you are visiting my channel first time, please do like, share and subscribe. Now let's start the video. In this first part, I will present brief introduction, geometry creation, OpenFoam folder structure for overset mesh simulations, and finally show animations of a simulation with linear oscillation of the object. Overset meshing, which is also called as Chimera Meshing, is a meshing technique in which multiple mesh grids overlap each other. This gives freedom to move, oscillate or rotate the mesh grids independently. This technique handles complex geometries and mesh dynamics easily compared to single mesh. In single mesh approach, creating non-conformal boundaries between stationary and dynamic meshes is easy for simple geometries, and it is highly difficult while handling complex geometries. Further to this, one suffers refinement restrictions for stationary and dynamic grid zones. On the other hand, overset meshing technique offers freedom to mesh different parts individually, allowing quality meshing and refinement. This also simplifies remeshing requirements in case of moving grids. Applications. This technique would be handy in dealing with multi-body dynamics in areas such as automotive, marine, aerospace, and specific applications involving fluid structure interactions. It may be further noted here that Overset Meshing module is not available in foundation version of OpenFoam. I could not find it. One may correct me if I am wrong. In this video, I am using OpenFoam2406 version of ESI group. I installed OpenFoam2406 version in Windows subsystem for Linux to work on these simulations. One may Google OpenFoam2406 and browse for the installation procedure. Now let us see the simulation domain considered to demonstrate the overset meshing. A rectangular capsule with two circular inlets on either sides is considered, with an opening on the top corner of a side. A closed manifold object is placed centrally within the capsule. As said, the overset mesh is created by merging the outer and inner grids, which are generated separately with individual refinements. This is the cross section of outer mesh, which can be named as background grid. This is the inner grid, which is termed as on-body grid. Now, after merging, the final overlap mesh can be seen like this. It can be observed that both the grids do have their own refinements. Now let us explore OpenFoam folder structure for overset meshing. As you know, basic working directory contains 3 folders: 0, constant and system. Whereas working directory for overset meshing needs different subdirectories as shown. The first folder is background. This is the main working directory of the simulation. This folder contains 0.org, constant and system, 3 subfolders. One may visit my earlier videos to explore files in each folder. Here in this particular simulation for overlapping, the 0.org folder contains, apart from the basic files, it contains zone ID and point displacement. The folder constant contains dynamic mesh dict. This file specifies the mesh movement, translation, oscillation, or any other type of movement. Further, the system folder contains, apart from other files, the set fields dict, toposet dict, and toposet dict underscore moving zone and extrude mesh dict files. I will discuss about these files later. The second folder is on body 1. So I named it as on body only for this simulation. In the current simulation, only one object is considered. Hence, I named it as on body. Based on number of grid zones, additional folders need to be added for individual meshing. The folder on body 1 contains constant and system folders. Only two folders. In this folder, the folder 0 is not needed as we only create mesh and merge it to the background mesh. As I told, the background directory is the main simulation directory. All final case settings are to be done in this folder only. All other directories such as onBody 1, onBody 2, or in other words, the foreground directories related to moving or dynamic grids contain only meshing details. The files required for overset meshing are: in system folder, we need two files, toposet dict and set fields dict. The toposet dict file is needed to define the cell zones and to separate the background and overset mesh regions. To do this, a cell set is created inside the file toposet dict. Now the other file set fields dict. In overset meshing, this file is used to assign zone ID to different mesh grids. In multi-phase simulations, this file is used to specify the value to a particular region, the scalar value for a particular region, 0 or 1. For example, 0 means air and 1 means water. The files required for overset meshing in constant folder, one file is needed, that is dynamic mesh dict. The motion properties of different zones are defined in this file. The library used for overset meshing is dynamic overset finite volume mesh. So this is the library which is needed for creating the overset meshing. Overset mesh boundary condition in 0 folder. This boundary condition is needed to exchange information between background and the overset meshes. The syntax looks something like this. This overset boundary condition is to be added in all the boundary condition files related to variables velocity, pressure, turbulence variables, if any. In 0 folder, two additional files are needed to specify the overset mesh boundary condition. The first file is point displacement. The point displacement boundary condition is specified in this file. We need to define overset boundary conditions for overset patch and moving patch. So for overset patch, the patch type is specified as overset and the type is 0 gradient. For the moving patch or the moving object, the type specified is calculated. Further, for all the stationary boundaries, the patch type is fixed value. It may be noted that for a symmetric boundary condition, the patch type would be empty here. Files required for overset mesh boundary conditions. Please note that in the video I referred the folder 0.orig as 0 folder, but basically it is 0.orig folder. The other file needed is zone ID. As there are two different cell sets, IDs or flags must be given so that they are identified as two different cell sets. This is done in zone ID. The syntax in zone ID looks something like this. Here, overset, the type is overset and uniform value 0. And for all the other stationary items, the type set is 0 gradient. Once we use the command restore 0 dir in terminal, the folder 0 is created. In this 0 folder, the file zone ID contains the zone IDs of different zones like 0, 1, 2, like that. I will compare the file zone ID from folders 0.orig and 0 to show the changes once we set up the case. Now, let us explore folder structure before launching the case. Now let us explore the folder structure. So this is, as I explained, there are two folders, background and on body. So first let us explore the folder background. Here we have 0.orig, constant and system. So in 0.orig folder, you can see all the boundary condition files related to pressure, velocity and the turbulent parameters. So let us open U. So here we can see, so this is the boundary overset boundary condition with type overset. Then all the other general boundary conditions are specified here: inlet 1, inlet 2, open, and this is the object which is treated as wall, a moving wall, and again the domain, the outer walls of the capsule, which is defined as domain with no slip boundary condition. Next, similarly, the file pressure. Here too, at the beginning you can see the overset boundary condition, then all the other boundary conditions are specified here similarly. Same is the case with turbulent parameter K. Here the first one is the overset boundary, and then the turbulence for all the other boundary conditions are specified here. The same is the case with NUT and omega. Now the main two other files for this overset meshing is point displacement and zone ID. Let us open point displacement. As I have explained, you can see here this is a overset patch with patch type overset. Then object is the moving object in this case. So we have here type calculated, and then all the other fixed boundaries are given as fixed value. Next is zone ID. So here in this file you can see overset mesh with overset uniform 0, and for other boundaries it is type with 0 gradient. You can see the format of this file zone ID in this folder. Now let us explore the folder constant. So here in this folder we can see folder tri-surface and 3 more files. So these two are transport and turbulent properties. The transport properties file, you can see the kinematic viscosity given here, and then we have turbulence properties. So here this is a turbulence model specified in this simulation. Now this is the dynamic mesh dict file. In this file, the dynamic moment of the object is defined here. So we can see here moving zone, and in this simulation I have given linear oscillation. So this is the oscillating linear motion, and this is the origin where the point center of gravity is specified here, and the amplitude in y direction is given as 0.1 and with omega 6.28. So this is the linear oscillation mode that is given to the moving object. There is a folder tri-surface In this folder we see all the STL files of the domain. So here these files correspond to the capsule, which is stationary domain. Now let us explore the folder system. In this folder, let us open block mesh dict. In this file, the vertices of the capsule are defined and the cell divisions in 3 directions are 30, 25 and 25 respectively with uniform spacing. The second file is control dict. This controls the simulation. This is the solver application. The start time, end time, delta t and all other parameters are updated here. Decompose par dict, as you already know, it is used for parallel computation. No need to check this file. This file exclude mesh dict is not needed here. This is basically to create mesh in the third direction, that is extrusion in the third direction. So in the current simulation the use of this file is not there, but I just kept it here. Let us open the file schemes, FV schemes. Here rest being same, the only thing is we need to add this part, overset interpolation. The method is inverse distance. There is no change in the FV solutions. All parameters remain the same. No need to change this. Now the file set fields dict. This is very important file here in this simulation with overset meshing. This is the default value. And then for different zones we need to give different cell IDs. So for the cell set C0 the zone ID is 0, and for the cell set C1 the zone ID is 1. So we have two zones, the moving mesh zone and the stationary zone. So that is zone ID 0 and 1. So all the cells in the domain either belong to cell set 0 or cell set 1. The next file is snappy hex mesh dict. This is explained already many times. So in this file the geometry for the background mesh should be specified here. So all the STL files related to the stationary mesh or the background mesh are given here. I am not explaining all the other parameters as they are clear. One may check my earlier videos to understand the use of these parameters. Surface feature extract dict. This file is needed to add the STL files here. Just the current STL files are to be updated. No need to change this inner part. The other important file is toposet dict. So here, as explained earlier, the actions are listed within this. You can see the name C0, this is the cell set C0 and the type is cell set. So here there are different types: points, point set, point zone set, and there are faces for which we have face set, face zone set, etc. And for cells we have cell set and the cell zone set. So here we can give any one of them. The action is new. There are different types of actions available, that is subtract, add, subset, etc. The source is region to cell. Again there are many sources. This is specific to the type given here. There are many options available based on the type. One can visit this website to check all these lists. So this is how this toposet dict file is written. So one can explore this website and see for clarity. Now the topo set dict moving zone, in this file just we are giving this part and we are specifying the moving zone here, that is the cell set 1. So now let us go to other folder, on body. Now let us explore the folder on body. Here we have two folders, constant and system. So in constant folder we have the folder try surface, within which we have the STL file of the moving object. Next, dynamic mesh dict. Here we are giving the details of the displacement Laplacian coefficients, that is diffusivity as inverse distance. We can use this file directly, no need to change anything here for any case. These transport properties and turbulent properties are same files as discussed earlier, no need to change them. It may be noted that this folder is additional folder and all the data given in the background folder only will be used, and here it is just added here. So no need to worry about these files. Now let us go to system folder. In this folder again we have block mesh dict. So here we specify the vertices of the object, rotating object here, and the number of cells in the three directions are 15, 12 and 12 with simple grading again. So in this folder the control dict file will not be used and no need to change any parameters in this. Again, decompose pair dict, this file also need not be changed, and the FV schemes and FV solution files also need not be changed. Now we go to the other file, snappy hex mesh dict. So in this file the only change we need to do is the on body or the foreground geometry, that is the moving geometry STL file has to be specified here. So for us the moving geometry is the object, so this file is updated here, and rest of the parameters remain the same. Okay, then here in this file also only that object STL file is updated and rest of the data is removed. So this is all about the folder structure for Overset Meshing. We have two folders, background and on body. Now let us explore this file, all run. Using this file we can launch the case. So here you can see first CD on body. So first it goes to, the compiler goes to on body, then it will run the simulation block mesh, then the application surface feature extract, and then snappy hex mesh. So once this is done, the on body mesh is done, that is the meshing of the rotating object or the moving object is completed. Once this is done, now it goes to the folder background. In this folder again it runs these three applications and meshing is created for the background mesh. Then both the meshes are merged using this command. Once the merging is done, we go to topo set, and then the log file of the topo set is removed. Once the topo setting is done, then the 0 file is restored. After restoring the 0 file, it will run the application set fields, and then the last command is this one. Once this is done, our meshing is completely done. Now let us open the terminal and launch this file to see how the meshing is done. Now open the terminal and set the path to the working directory. So here we can see two folders, background on body and the file all run. So as I told you, we are running the simulation in OpenFoam2406. So we have to first select the OpenFoam2406. For that, we write OpenFoam2406, then enter. Now the compiler OpenFoam2406 is active. Then using the bash command, so let us launch this file. So now it is creating the mesh. So finally everything is done. Now let us see whether the meshing is done correctly or not, whether the boundary faces are selected correctly or not. Now first we go to on body. Now here open constant folder. See here two folders are created. Go to polymesh and then open boundary. You can see here object. So the boundary condition here is selected correctly. If there is any mistake, then here you will see all boundaries. So that means the correct boundary condition is not selected. So we have to check the mistake and rectify it. So now it is fine. Now we go to background folder. So here go to constant folder. Again here two folders are created. Open polymesh and open this boundary. So here we need to see all the boundary conditions. So open inlet 1, inlet 2, domain wall, and finally the object. So no unknown boundary is present here. So the meshing is done correctly and all the boundary conditions are selected. As I told you earlier, now the 0 folder is created. Now compare the files here. In 0.org file, you have file zone ID. Open this. You can see here this much is written. Now let us open the file in 0 folder, the same file zone ID. Now you can see here the difference. In 0 folder, the file zone ID contains the IDs of the cell zones. You see 0, 0, 1, and then you see all the other boundaries are written here. This is a modification done by the compiler. Okay, but in 0.org folder, the file zone ID contains this much data only. So this is the difference. Once this is done, now the simulations are correct. So finally the meshing is done. All the boundary conditions are selected correctly. Then we can launch the case. So for that purpose, we go to the terminal again. Now what we do is we set the terminal path to background. Now here we use the command over pimple dym foam and launch the case. So the simulations are started. I have set the time for 5 seconds. Once the simulation completes, I will show the animations. Simulation completed in 4 hours. Results are loaded in ParaView and the following animations are created. The linear oscillation of the object is animated and presented here. Here this is the cross-sectional view and this is the complete domain. So finally, in this first part, I tried to explain the procedure to set up overset meshing in OpenFoam 2406, the ESI version. In second part, I will show the procedure to set up rotation of the object. So stay tuned. Please do like, share and subscribe, and do not forget to click the bell icon. Thank you very much.